Welcome to the last section of Chapter 12, and the last section we'll be doing before our exam. It's only a section we're doing this week, and then we have the exam the following week. So there should be some time to really study and get going, get everything in order for the exam. This section won't add too much onto us that's heavy. There are some concepts being discussed, but they're founded in the previous sections. There's no new strong material. So let's talk a little bit about what's going to be in here. The first thing that we want to talk to you about is what's called the normal distribution. So the normal distribution is a very special distribution. If you were taking a regular stat introduction to statistics class stat 300, we would spend about half of our time using the normal distribution to solve things, and so it's a pretty big distribution. Here's what you want to know about it. It's bell-shaped. Okay, so the distribution looks like this. It's a bell-shaped distribution. The data kind of starts slow, peaks in the middle, and falls off. And right in the middle is the mean. The mean lies right in the middle of a normal distribution. So I'm trying my best to draw that completely symmetric around that line. I know it doesn't appear that way, but a bell-shaped distribution is perfectly symmetrical around that center line. And what's interesting is if you have a normal distribution, then the mean, let me write that out a little bit better. Then the mean, the median, and the mid-range all are the same. Okay, they're all equal. They are all equal to one another. So if you truly have a normal distribution, the mean is equal to the median, which is equal to the mid-range. So pretty interesting. So I know there's a homework question like that. Also, when you have a normal distribution, one of the reasons why we want to bring it up is because of the work that you've been doing with the mean and the standard deviation. So when you have a normal distribution that's centered about the mean, right? So put the mean right in the middle. If you go one standard deviation out, so I'm just going to put a 1 SD, SD standing for standard deviation. One standard deviation in either direction, you capture a certain amount of data. So I'm going to use, because I can, a highlighter, and I'll highlight it in blue. I like blue. So I'm going to come in here and highlight this area. This shaded area right here is data that's within one standard deviation of the mean. And if you're within one standard deviation of the mean, there is about 68% of the data lies in there. Now you dealt with Chebyshev's theorem in the previous sections. This is what they call the empirical rule. So the empirical rule is for the normal, distribution. Okay, and what it says is if you go one standard deviation out, you capture 68% of the data. So before we just throw on other stuff, let's make sure we really understand that. So what if I told you that the average on the first test was 73 and the standard deviation was 5, and the scores were normally distributed. So when I say normally distributed, I mean it's following that bell-shaped curve. So the scores were normally distributed, the mean was 73, and the standard deviation was 5. So if I draw a picture of the distribution of test scores, It'll be a bell-shaped distribution with 73 right in the middle. And if you go 5 out in each direction, 78, and drop down to, what would that be, 68, then we would have had, but notice that that's moving out one standard deviation. One standard deviation away from 73 is 78 above and 68 below. So we would have been this area right in here. 68% of the scores would be in there, which means that we have some left over, right? So what's left over? What's 1 minus 0.68? So 1 minus 0.68, that's 32.32. So 32% of that. So 100% minus 68% is 30%. That's the other way I could have done it, is just kept everything in percentages. Hey, 32% is left over. Well, what's half of 32? Well, that's 16. So just so you know, I'll put it in red. 16% of the data was above 78. 16% of the data was below 68. Right? So those are all things that we can infer from that. But 68% of the data is right in here, okay, in that blue area. That's what we're saying. So within one standard, let me go back to the black. Okay. Within one standard deviation of the mean lies 68% of the data. So I'm just restating what we said above. I just wanted to make sure we understood it because they're going to ask for it in different forms. So this is for a normal curve only, right? This is the empirical rule on a normal curve. Within one standard deviation, 68%. Within two standard deviations of the mean lies 95% of the data. And within 3, and that you'll see why we stop at 3 standard deviations of the mean lies almost everything, 99.7% of the data. Okay, so I saw the homework, and sometimes they ask you to round to the nearest whole percent. So the first two are already there. They'll round the 99.7 to 100%, right? They'll do natural rounding there. So don't be afraid to plug in. About 100% of the data lies within that. And so they'll ask questions that are related to that. So some of the questions I saw were like this. One was actually a test. Scores on a test are normally distributed with a mean of 83 and a standard deviation of 3. What percent of the data lies between 80, I apologize, I have my numbers wrong, so let me come in here. The mean was actually 77. Lies between 83 and 89. Okay, so scores on a test are normally distributed with the mean of 77 and a standard deviation of 3. What percent of the data lies between 83 and 89? So let's draw a picture. A normal distribution. How do we know that? Because they say it's normally distributed. 77, and I got two values, 89 and 83. Now, how far are they away from 77? So as we consider that, how far away is 89 from 77? Let's find out. 89 minus 77 is equal to 12. I must have wrote that down wrong. Yeah. Maybe I did have the right mean. I apologize. I had the right mean in the beginning. What I'm writing doesn't make much sense. It's because I did have the right mean. I just wrote down the numbers funny. So 80, 83 is the mean. So going back here, sorry about the mess up. So 83 is the mean, and they want to know between 77 and 89. So take a look at the difference. Between 83 and 89, we have a difference of 6. Between 77 and 83, we also have a difference of 6. Now, that difference of 6 is special. 6 is 2 times 3. Now, why do I care that it's 2 times 3? That's 2 times the standard deviation. So this is 2 standard deviations. This whole distance right here, I'll highlight in red this time because it's different than we had before. This area in here, they want to know what percentage of the data lies within there. Well, you're going out 2 full standard deviations. Well, if you're going out 2 standard deviations, we just have to look at our chart that we'll bring with us or memorize, and we know that the answer is 95%. 95% of the data lies between those two values. So they'll pick things that are equally spaced apart and then ask about that. And they'll stick with either 1, 2, or 3. If it's 4, just say 100%, right? And so that's what they're going to have there. They might also ask a question like this. On the ACT exam, the scores were normally distributed with a mean of 25 and a standard deviation of 3. Sorry about touching there. So I got this from the homework. What percent of the values lie above 28? Okay, so let's talk about that. So we're going to be using the empirical rule. What we have is a bell-shaped curve because they're normally distributed. 25 right in the middle. They're asking about 28, and they want to know what's this area up here. So they want to know this green area up here. What's that area? Now, what do we know? Well, let's first of all figure out how far away 28 and 25 are. The pure distance between there is 3, which is 1 of the standard deviations. So we're 1 standard deviation away. So what do we know? We know within 1 standard deviation of the mean lies 68% of the data, with the leftover 32 split up. So what is this up here? So we saw this before, but 100% minus 68% would be 32%. Now, where's the 32%? The 32% is here and down here. It's in those two tails combined. So half of it's in the upper tail. So this is 16%, and we're answering 16% coming through. They wouldn't arbitrarily pick a number. So they're going to either pick 28 or 31. Now, why would they pick 31? What if this problem changed? Before I make that change, I hope you're okay with the 16%. So we use the fact that it was 1 standard deviation away, and within 1 standard deviation from the mean is 68%. Because the normal distribution is symmetric, the leftover 32%, half of it would be above 28, the other half would be below 3, below 25 or 22. Here's the other 16%. Now they were asking about this 16%. So what would change in this problem? This is kind of why I like my iPad. Let's just get rid of all of this for a minute. Get rid of these pictures here. And then change some things. What if it wasn't 28 that they had, but they had put something like 31? Now, I didn't arbitrarily pick 31. How far away is 31 from 25? Well, it's 6 away. Why is 6 special? Because in this case, it's 2 times the standard deviation, because the standard deviation is 3. Well, we know that if you go 2 standard deviations out, you capture 95% of the data. 100% minus 95% is 5%. Well, 5% is what's in the outside 2 tails combined. We only want one of them. We only want this guy, which represents half of that 5%. So I got to take that 5% and divide it by 2 to get 2.5%, right? You'll have your calculators. This is 2.5%. That's your answer, is 2.5%, half of 5%. So they're going to be asking questions like that that get you familiar with what's called the empirical rule. That's a majority of the homework. The only other thing that happens, and it's right up front, they ask about the normal curve, and then they ask about continuous data or discrete data. So there's maybe 3 questions or so that deal with continuous data or discrete data. So I need to define them. So they're just going to basically talk about some data and say, is this discrete or continuous? And what it's describing is the type of data. So I'll start with discrete data. Discrete data is finite or countable. Okay. Lots of data is discrete data. So for example, the number of students in a class, if that was the data set that was being collected, that is a discrete data set. Because is there anything between, if I told you there's 24 students, do you know the very next one? And the answer is yes. The very next one is 25. That's discrete data. If you can tell me the very next one, then it's discrete. So discrete can check it off. So number of hotel rooms, right? If they were looking at data that was hotel rooms. Even price is discrete, right? Because what's after $19? Well, it's not arbitrary. The very next price that can be charged is $19.01. So as long as you can tell me the very next one, it's discrete. When you have continuous data, is infinite and cannot be counted. Okay. So, got to be careful about that. I'm not talking about you don't have enough time to count it. So, for example, sand on the beach is actually discrete, because what's right after 5 grains of sand? 6 grains of sand. What's after 1,000,000 grains of sand? 1,000,001 grains of sand. You know the very next number. That's discrete. So it's countable definitely means infinite as well. It just means you can count it. So continuous data cannot be counted. That's the big key there. So for example, if I told you that my weight was 175 pounds, you cannot tell me the very next one. Because if you say 176, I'll say, well, what about 175.1? You're like, oh yeah. And then, so that's the next one. Well, I'd say, what about 175.01? Oh yeah, so that's the next one. Then I'd say, what's 175.001? And they'll operate off of theoretically what's possible. If I had a tool that could measure it, I could get weight out to that many pounds, right? And so things like weight, height, distance, those are all discrete. Any one of those is discrete because you can theoretically measure it to the infinitesimal degree. And so that's I apologize. That's a continuous setting. I might have said discrete just a minute ago. All three of these are examples of continuous data. Discrete data, you can tell me the very next one, but the next weight after 175 can be anything. You give me a number and I'll give you something in between, and we can play that game forever. So temperature is another one that is continuous because it can be measured out to the smallest degree. Volume is continuous. So lots of continuous things. So they're going to give you some examples and say, is this continuous or discrete? And we don't want it to, I was going to say it's a 50-50 shot, but we don't want you guessing. Analyze it and say, okay, let me just make up a data point like I did with the students, 24. Okay, what's right after 24? 25 students. Okay, let me make up a temperature, 100 degrees. Okay, what's the very next one? 100.1. Well, no, maybe 100.01. Oh no. And so you just keep going and going, and you realize, oh, I can do that forever. That's continuous. So measured things are usually continuous. So let that be your guide in 2.5. That's really it. There's only 9 questions as you go through and do that. Next week should be a nice breather, but use it as a time to prepare for the exam.